So are there any questions? They will modify your stiffness matrix and also right hand side. Modification in the stiffness matrix. Because of the contact conditions, the stiffness matrix will change. And right hand side can also change now depending on because the force contribution. So the simple problem is now like you have contact between the two surfaces, so they should not penetrate. So the normal displacement of now this surface must be equal to normal displacement of this surface. So if they were just free, you have a different stiffness, overall assembled stiffness. If you impose this condition that the normal displacement of this surface must be normal displacement of this surface. So now this is becoming normal displacement is common to both of these. So accordingly your stiffness matrix actually gets modified. So then it depends how you impose these conditions. One of them is penalty approach. So we add again some term into the stiffness matrix, or you use Lagrange multiplier approach. So there are different ways, but ultimately your stiffness matrix basically changes with the imposed contact conditions. So of course that we are not doing in this course. So these are basically topics of advanced FE course. So let me then start. So last class we were discussing about the solution of simultaneous equations. So of course what we are discussing is very brief, and then the next we were discussing about this conjugate gradient method. So last class I think what I had done was, so I'll just summarize maybe that and then continue. So here what we are doing is we are saying that when we want to solve this system, that is matrix A into D is equal to R, let us say we want to solve this system. So this is equivalent to minimizing, that is what we have already said this. So this is equivalent to minimization of functional consisting of all these terms here over D. Then minimization is equal to an integral functional, say I, which is half of, you can write that as D transpose into A into D minus D transpose into R. So this is, if you recall, this is actually nothing but our integral functional for all linear problems. So we are, rather than now first deriving the set of simultaneous equation, now we want to minimize this integral functional. Of course this is for the assembled system, that is what we are talking about. So now rather than solving this, we are trying to minimize this functional, that is what we do in the conjugate gradient method. So I had said that the approach in this is, first we start, so you assume the starting guess is say D as D naught. So you take this as your starting point, and as I was saying that this could even be a null vector. So that means your starting guess could be just a zero displacement, zero values of all the degrees of freedom of the whole vector. Then you calculate the steepest, at the starting point you are actually using steepest descent method. That means you are from the starting point you are moving towards the minimum along the highest rate of decrease of the function direction. So that is we call as the steepest descent direction corresponding to this. So I think I had used a notation R naught for this. So R naught is nothing but negative times of the gradient, so minus of Z naught, and G naught I had told you that this is basically going to be minus of, so if you know just the derivative of this with respect to D is actually going to be this AD minus R, and negative of that is going to be basically R minus AD naught. So you can write that as R minus AD naught. small d anything. So this is R naught. So what you do is make an initial guess, then at that initial guess you calculate the gradient, and my negative times are the gradient, that is the highest basically the direction in which there would be highest rate of decrease of this function I. So R naught is you set as minus G naught, which is R minus A into D naught. Essentially G itself is A into D minus R, so minus of that becomes this. Then we find the do a line search, what is known as, so we want to move, so it's something like the function is having minimum somewhere, and then these are the plots of constant function values, we call these as level sets. So we are starting from say somewhere here, this is our starting guess, and then we are moving along a direction which is essentially going to be normal to this surface at this point. So we move, and then we move see beyond that, if you reach up to this point, after that the function value again will start increasing. So you call this as say alpha naught. That's the first step, because we are starting from the first step. That's the notation I use. You can also say alpha 1, but I used it as alpha naught. So then what you do is the new solution. Now starting from this initial guess, the new solution would be, let us say we call that as D1. So new solution is vector D1, which is equal to initial guess, in this case the D naught, and plus alpha times, so this alpha naught times that means we are moving of, this is our D naught point here, and now finally we want to go to this point which is D1, vector D1, and we are moving in this direction, that is from D naught to D1 by a distance of alpha naught. So this step of finding out alpha naught is known as line search in optimization. That means along this line you want to line search, meaning is we want to find a point where the function is minimum, but that search along a line, so it is referred to as line search. So we want to go reach to this point, so that is D1 is D naught plus alpha naught into this direction is R naught, that is vector R naught. So this is what we did in the last class. Then now we want to find, so this is your new solution, but this solution is not at this is known because this is your initial guess, and this because you have calculated the gradient at initial guess, but the alpha naught is not known. So then you need to find, I think many students even don't know where are their classes actually, even till the end of the semester. Maybe he must have slept, maybe I don't know, but whatever time I might have got right now only maybe about half an hour he must have wake up, and then he's just coming, so even forgot where the class is. So that is the problem actually, isn't it? So now see, you want to find out alpha naught. So how do we find alpha naught? So this solution you are going to substitute in the this functional I here, and then find out the di by d alpha equal to 0. So essentially you do that. First order necessary condition for I to be minimum with respect to alpha is di by d alpha naught equal to 0. And of course when you take the second derivative, so that is just going to be matrix A, and we are saying here that A is positive definite matrix, so this will always lead to a minimum of the function. So we will be approaching towards minimum. So when you do di by d alpha naught, so this is where I had written the equation. So did you derive the expression for what is alpha naught finally? So now you are substituting this in the I. So if you look at the expression for I, what you are doing is now in place of d you are replacing d1, and then you are differentiating it. So the first in I, the first term is half of d transpose into A into D minus d transpose into R, and that d now is actually replaced by d1, which is having alpha naught. So you are going to differentiate that. So I think that I did in the last class, you recall that. So we had half, and then the derivative, the first one with respect to alpha naught, which will actually give you R naught. So we will have R naught transpose into A. This I had done, you can refer your notes. And then here of course we have this entire d1, which is d naught and plus alpha naught into R naught. So this is one term. That means I am saying the derivative of first into second plus first into derivative of second, which is R naught plus d naught plus alpha naught times R naught transpose into A, and then the derivative of the second. So then because the derivative is with respect to alpha naught, that is scalar, so this is constant, and this only will give you simply here R naught, and then you have that D transpose into R term. So the derivative of D transpose would be simply R naught transpose into capital R, and this must be equal to 0. So this is di by d alpha naught. So in the expression for I, substitute first this d as d1 and then differentiate it with respect to alpha naught. This is what you will get. And now if you simplify this, now you can just try to simplify. So what do we get? So you see that one is that this is R naught transpose A into this whole thing, and this term is the transpose of this into A into R naught, and since final product is a scalar number, so yeah, you can write one expression as the transpose of the other. So finally one can write this term essentially as equal to this. That means you can replace this by its transpose. What I am saying is this can also be, the whole expression can be written as its transpose. It is one and the same thing. Once you open this transpose, so like ABC whole transpose is C transpose, B transpose, A transpose. A is symmetric, so you get R naught transpose into A transpose, which is A into transpose will become this. So finally this will be simply R naught transpose into A into D naught plus alpha times R naught. So that's what these two terms can be combined together. So this is same as when we were deriving the element level governing equations and we were taking variation. So this step is same as that. We get two terms and one is term is same as the other, so we replace by its transpose. So you finally half goes, and this is what you get, and this you get as minus R naught transpose into R is equal to 0. And now we want to find out basically alpha naught. So what would be the expression for alpha naught? Yes, expression for alpha naught from here, you just have to first term is R naught transpose A into D naught, and then second term is so let me write. So finally what you are going to get is this side is R naught transpose into capital R, that I am taking to the right hand side, and this term also to the right hand side. So minus I will get R naught transpose into A into D naught, so divided by this term, which is R naught transpose into A into R naught. So this is what you get as your alpha naught, isn't it? And now if you look at, see essentially if you see this R naught transpose, then if you take it as common, so what you get is inside R minus A into D naught, which is nothing but your R naught itself. So actually numerator you would see, is this okay? So the numerator is simply R naught transpose into R naught, and of course the denominator remains same as R naught transpose into A into R naught. So this is finally is your alpha naught. Once you calculate alpha naught, then in your solution space, this new point, so you would reach here. So because then you put the value of alpha naught here, you get the new vector, and this we are now trying to do iteratively. So the advantage here is, see if you look at the calculations, the first step we would need to do actually this calculation. So here what you are doing is matrix vector multiplication, and again if you are looking at this place, so this is vector, numerator is vector multiplication, and denominator is matrix vector, and then with the vector multiplication. So no inversion of a matrix is involved, and multiplication is vector matrix multiplication is computationally is of the order of n square floating point operations, whereas inverse of a matrix is proportional to n cube number of floating point operations. So for large size systems, inversion of a matrix becomes computationally more involved, whereas this would be less involved, n square. Let's say if you do 1,000 square and 1,000 cube, so it's going to be that many times the difference in the number of floating point operation, and therefore computational time. So this is the first step. So we get this alpha naught from this expression like this, and then get the new solution. Once you have got D1, then we construct now new search direction. So new search direction, now what we are doing is that no, we have reached to this point. If we were using steepest descent direction, then in that case we would be actually moving like in this direction somewhere here, and maybe then steepest descent we would encounter another minimum along this direction, then we will go up to that point. But what we do in case of but the drawback of steepest descent is when you approach towards the minimum, convergence becomes slower. So then what you want to do is you want to combine these two directions together. So now a linear combination of this direction and this is taken as a new search direction, and with that you can get the faster solution. So that is basically the aim. So in conjugate gradient you don't want to go along this direction, but you want to go along a direction which is combination of this and this. So that is basically this direction. So now we construct a new search direction. So that is new search direction. So there are always two things, search direction and then the line search, finding out the value of alpha. So new search direction is taken as combination of steepest current, steepest descent direction and previous search direction. So that is now the new see, we had here the direction R0. Now let me call that as R1. So R1 would be taken as, I am going to take it as a steepest combination of this current steepest descent direction. So this would be minus G1, G0 I have used if you remember for the gradient here. G0 is the gradient at D0 and G1 is the gradient of phi at now D1, because now you have got a new solution. So this is minus G1 times some scale factor, so let me call that as beta, you can use any notation, times the previous search direction, and previous search direction is basically this R0. So this is now combination of current steepest descent direction, that is essentially this, which is minus G1, and then this is plus some factor into R0, which is the previous search direction. And now this process you continue. So now this is going to be and obviously here R0 you know already, and your G1 vector, see G1 is nothing but a into, you have got a new solution minus capital R. So this is your G1, minus of that is R minus a d1. So this is your R1. But now the question is, we have introduced one more scalar parameter, that is beta 1. So we need to find that. So what would be the value of beta 1? Now as the name suggests, the name of the method is conjugate gradient method. So here what we do is all the search directions are conjugate to each other, means actually they are orthogonal to each other. So we find beta 1 such that R1, now right now we have previous search direction R0, the current search direction is now R1. So we find this beta 1 such that R1 and R0 are orthogonal to each other with respect to, so let me just put WRT. So with respect to matrix A. So it is not just R1 transpose into R0 I am going to do, but what I am saying is you do this as so this implies that the condition is R0 transpose time in between matrix A, because we are saying orthogonality with respect to A, so in between A into R1 is equal to 0. So this is the orthogonality condition. So we are saying that this product R0 transpose into A into R1 equal to 0. So this is what is written here, that R1 and R0 are orthogonal to each other with respect to matrix A, which is your symmetric positive definite matrix. And now using this we can actually find out beta 1. So now you put the expression for R1. So as you see here, this is R0 transpose into A, this you keep as it is, and you see as far as this R1 is concerned, So R1 I can write from here, which is say minus of G1 times beta 1 into R0. This is equal to 0. And now you know solve for beta 1. So can you tell me what would be the beta 1 quickly? So the first term is R0 transpose A into minus G1. So I can say that beta 1 is going to be, when you take this to the right hand side, you will get R0 transpose into A into G1 and divided by what you are going to have is R0 transpose A into R0. So this is your beta 1. So once you calculate beta 1, then you have actually your R1 direction. What you can actually see that if you slightly manipulate this expression can actually be written as G1, that is gradient transpose at D1. So G1 transpose into G1 divided by G0 transpose into G0. This proof I leave it to you. So in fact this can be, why we want to do that, because then this involves only vector multiplication, so you save computational time in that. So this expression whatever is written here for beta 1 based on this orthogonality condition can actually be just expressed in terms of the this dot product of inner product of gradients G1 transpose into G1 upon G0 transpose into G0. So once you got beta 1, then you got your R1. Now you have to construct a new solution to essentially, so therefore the now next new solution is going to be, so let us say new solution I will call it as D2. So then D2 is going to be D1. D1 you have already calculated here, because once we solve for this alpha naught and then we put that alpha naught here and we get this D1, and now we want to get the new solution using new search direction which is given by R1. So it would be D1 plus, say I will call it as alpha 1 times R1, and R1 now you know because everything is known in that. So it is simply, let me write it as R1. So now the actually this is new search direction and you need to find alpha 1. So once you find alpha 1, then you know the new solution. And if you want to look at actually this proof is a small modification replacing essentially R0. So what you can do is like here if you have written this R0, you can write it as D1 minus D0 by alpha naught. So you replace R0 by that. So then you get difference of D1 and D0, and that can actually be written as in terms of gradient G1 and G2, and then if you do the manipulation you can finally get to this. So I given a hint, you can actually try that. So this is D2, and now only we need to find this alpha 1. So how do we find alpha? Again minimize. So now you need to find alpha 1, and that is by minimizing di by d alpha 1 equal to 0. And so as we have done earlier, the solution is going to be similar. Now, you will get, you can derive the expression for now what would be your alpha naught for this particular case involving this. So as we had seen earlier, this gives rise to essentially R1 transpose into say A into, here we will have D1 plus alpha 1 into R0. This is the first term, and then the second term we had this R1 transpose into capital R is equal to 0. So this is similar to in place of, now you have I, which is D2 half of D2 transpose into A into D2 minus D2 transpose into capital R, and then differentiate that with respect to one unknown, that is alpha 1. You get this equation, and now you express using this equation, you write your alpha 1. So which would be simply R1 transpose, as you see here, R1 transpose into, one is capital R because this is going towards the right, and minus this which is essentially minus A to D1. So this is what you get, and what you will have in the denominator is then we are going to get this R1 transpose A into R0. Is that right? Yeah, why did I write R1 here? No, R0. This is actually R1, I'm sorry. So this is R1 here, so you get R1 transpose A into R1. So again you will find that R1 of course is, as you remember, no, this is your search direction what we got here, no, that R1 is this, which is combination of these two. So you can finally write this, and again if you look at this capital R minus A into D1, this is actually, no, you can say nothing but negative times of essentially G1. So you can write it in terms of G1 finally. So numerator will be only vector vector product, whereas the denominator is no, matrix vector and then with a vector. So like that, no, you continue. So the next iteration, continue the iteration like that. So you can continue the iteration till two consecutive solutions are close in a certain manner. Two consecutive solutions are close enough. So this is known as conjugate gradient method for finding out the solution of simultaneous equations. So what is the advantage there? The computational time for large size problems is much less compared to even for example we were trying to do the Cholesky factorization or any other inverse method you use. Compared to that, this would be computationally much faster. So that is the advantage of this. Of course, there are improved versions of this. Is known as preconditioned conjugate gradient solver, and you will find in many of the packages actually this solver would be there. And there are others. So there is even the Lang-Sauce method for finding out the solution of simultaneous equation. Also, similar thing is there for eigenvalues. So and GEMRES and so many other things. So if you want to learn more about that, you have to do a lot of reading. So I just want to stop here and then continue about the eigenvalue problems. Now in case of eigenvalue problems, see what in general case what we want is, as we had discussed in the last class, know that we want to find out the natural frequency, say omega n into m. This is the eigenvalue problem we had written, where this now dn is the essentially eigenvector and this is the eigenvalue is equal to k is the stiffness matrix into dn, where here omega n is the natural frequency and there are going to be n number of natural frequencies. This is small n is for natural. So this is natural frequency. If you evaluate it as it is, this would be actually in radians per second, and dn is the modal vector, or you simply call it as mode shape. Now the solution here means we want to find out the set of values, say omega n and dn, corresponding dn. That's the solution of an eigenvalue problem. And what are the algorithm, how we can think about it. So before that I discuss some of the algorithms. First I'll demonstrate what is known as orthogonality of mode shapes. So suppose if I consider orthogonality of mode shapes. So if you look at, let's say if I consider two eigenvalues and corresponding eigenvectors, say omega I di and omega j and dj. So for ith eigenvector I can write similarly this equation as, say, omega I square into m into di is equal to k into, see, in place of n I am simply writing I, which is one eigen corresponding to ith eigenvalue and corresponding eigenvector di. Omega I gives you natural frequencies, that is if the structure is disturbed in that particular mode, it is going to vibrate with that frequency and that particular shape. That is, shape is determined by di and the frequency of oscillation is governed by omega I. So this is into di. So this is the equation governing ith eigenvalue and corresponding eigenvector di. Similarly, if you consider another mode, say jth mode, so corresponding eigenvalue is omega j. So the governing equation would be omega j square m into dj is equal to k into dj. Now we want to prove here that di and dj, they are orthogonal to each other, again with respect to k r m. So how we can show that is, for example, now if you multiply by dj transpose in the first equation. So let me do here dj transpose. So I am multiplying this whole thing by dj transpose, and if I multiply the second one by di transpose, the whole equation here. What do we get if we do this operation? So see, if you look at the first one is going to be as if you look at is the first equation would give you omega, because it's a scalar, I can take it write it anywhere. So omega I square, you will have here dj transpose into m into di is equal to, the right hand side you are going to get again dj transpose into k into di. That is the first equation. The second equation would become, now I can similarly take out this omega j square, so I can write that as di transpose into m into dj is equal to, this side you will have di transpose into k into dj. So the first one is multiplied with dj transpose, you get this, and second one is multiplied with di transpose, you get this. Now since this again finally if you look at this, maybe k would be something like is a, let us say, capital N by N matrix, this is N by 1 vector, and this is transpose means 1 by N. So finally this multiplication is going to be a scalar number. So if you look at these two, this is dj transpose k into di, and the second one is di transpose k into dj. So if you write, let us say this by its transpose, and which is going to give you finally the same number, but then when I take its transpose, it is same as this. So if I, let us call this as equation 1 and this as equation 2. So if I do 1 minus 2, what do I get? Equation 1 minus equation 2 will give us, now this side, as I said, because I am writing the second one as its transpose, so the 2 will actually get cancelled out. And similarly if you look at here, this is dj transpose m into di, and this is di transpose m into dj. Again this multiplication is a scalar number, similarly this is also a scalar number, so I can write one as the transpose or the other, but only problem here is that you have omega I square multiplied here, omega j square multiplied here, so I cannot cancel them out, so they will not cancel in general as long as omega I and omega j, they are different. So but I can write this term same as actually this term. So I when I subtract, so what I will have then, omega square minus omega j square, and then this you can either write this way or this way, both ways. So di, both are valid, di transpose m into dj. So what I have done is essentially here written the first one here as its transpose, so it becomes same as this, and that is taken out here, so you get omega I square minus omega j square. The right hand side actually becomes 0, because these two terms are same when one is written as transpose or the other, so they are essentially same quantities. And now if you look at this expression, so now if we have a condition that if omega I is not equal to omega j, in that case now if this has to be 0, whatever we have on the left hand side, so that means then di transpose, if this is not equal to 0, that implies that di transpose into m into dj, this must be actually equal to 0. That this is what is known as, same thing we were doing in the conjugate gradient method. So same thing there, we said that the two consecutive search direction must be orthogonal to each other with respect to matrix A there. Here same way we are saying that mode shape corresponding to eigenvalue omega I and mode shape corresponding to eigenvalue omega j, they are orthogonal with respect to mass matrix. So that is di transpose m into dj, that's equal to actually 0. And this is now orthogonality with respect to mass matrix. Once you have this, so then you can also say, because now you are saying here that if you take any one of these equations, so we are saying that dj transpose m into di is actually equal to 0, or di transpose m into dj equal to 0. So from this we can also say that once you derive this, then this also implies that the mode shapes are orthogonal with respect to stiffness matrix also, because on the left hand side if I take either this or this, that is 0, so therefore this would be equal to 0. So this also implies that di transpose into k into dj, this is also equal to 0. So that means your modal vectors are orthogonal to each other with respect to mass as well as stiffness matrices. Here that is di, you can write either di transpose m into dj, or you can write dj transpose m into di. This will be, as long as I and j, omega I and omega j are not same, the di and dj, they are going to be orthogonal with respect to each other, with respect to both mass and stiffness matrix. Just a mention about this property here is, I also want to tell you that actually most of the problem wherever you know the stiffness, element level stiffness, let us say, is in the element local coordinate system is constant spatially. So even you will find that di transpose into dj will also be actually equal to 0, or dj transpose into di will be 0. But if you have a variable stiffness structure where the element level stiffness matrix is changing from one location to another location, so there you may not find di transpose into dj equal to 0, but with respect to mass and stiffness, this will always be true. So one example I can give you, when we were working on a problem on non-circular cylindrical cell. So that's an example. So it's like you have a non-circular cylindrical cell. I just want to talk about this property because typically you don't find that in books. So this is let's say a non-circular cell means you have a cell which is essentially a cross section is a non-circular cross section. So for such cross sections, because the radius of curvature is, if you are looking at this, so here if you see that radius of curvature is very high, whereas here that these corners, these ends of the semi major axis, the radius of curvature is very small. So here actually this structure you find would be more stiff, here it would be less stiff. Because of the more curvature here, it's more stiff, less stiff. So there is a variation in the stiffness along the circumferential direction. So for this case, you will find your eigenvectors, and then if you just try to take the this say di transpose into dj, that would not be 0. But when you say dj transpose into m into di, or dj transpose k into di, you will always find that that would be equal to 0. But if I take a circular cylindrical cell, where the stiffness is identical everywhere, and you get the modes, and if you just look at different modes, dj transpose di would be equal to 0 for this case. So you not only there, without even including the mass and stiffness matrices here in between, you find that the mode shapes are actually orthogonal if the stiffness matrix of the structure is constant spatially. But for the problems like this, the modes are orthogonal with respect to mass and stiffness only. They are not orthogonal with respect to themselves without including m and k in between. So this is known as the orthogonality property of mode shapes. And then next is we sometimes make use of this property to find out extract the eigenvalues and eigenvectors of a given problem. So how do we make use of that? So like if I construct, let us say, a matrix, let us say let me call it as T or some phi. I mean, let us not call it as let me call it as a modal matrix. So if I construct a modal matrix means this is the matrix, let me call it as phi, consisting of all your eigenvectors of the given problem. So this would be consisting of say d1, d2. So each eigenvector you are taking and putting as one column. So d1 is first column of this matrix, d2 is the second column, d3, and so on. You finally will have n eigenvectors of the whole system. So you will find that this would be a n by n matrix. That is d1, d2, d3 up to dn. If you put all the eigenvectors into this as a column vectors, and of course each one of these is n by 1 vector, so you will get n by n matrix. So this is known as modal matrix. That is matrix consisting of modal vectors or mode shapes, d1, d2, d3 and dn, so on, dn and this so on. Now if you actually multiply, what you will additionally what you can also do is, suppose we construct this phi such a way that this phi transpose m into phi is an identity matrix. So we can always scale each of these eigenvectors. So additionally, let me also say that this modal matrix transpose into M mass matrix into again this modal matrix. Let us say this is identity matrix I. I is a n by n matrix. So these are capital N by n matrices. So finally, this is n by n. This is n by n vector matrix. Sorry, not vector. These are all matrices. I am putting the modal matrix here. So this is also a matrix. and this is also transpose is also n by n. So finally this is going to be n by n matrix. This is n by n identity matrix. So we make sure, because the modes are orthogonal, so only the diagonal elements are going to be non-zero. That is why no d1 transpose m into d1 would be non-zero, d2 transpose into m into d2 would be non-zero, but all other combinations would be 0. That is d3 transpose m d3, they are going to be non-zero. And we scale these eigenvectors. Say I get, initially I get the eigenvector which is arbitrary, then I do the multiplication d1 transpose m into d1, I get some number, square root of that I divide by the whole d1, and then finally get d1 transpose m into d1 as identity after that division. So finally you have this as the identity matrix. So once if this is the identity matrix, then you will find, if I look at the this multiplication of k, that is, now let me see this phi transpose k into phi. Now what do I get this? Now my phi is such that phi transpose m into phi is equal to I, and phi transpose k into phi then would be, this will be simply again a diagonal matrix, and with omegas as the omega squares as the diagonal element. So I will have here omega 1 square 0 0 like that, 0, omega 2 square 0, and so on, and like that. So this is omega 3 square. So this is what you will get. So this, if one is that these model all the model vectors d1 d2 they are orthogonal to each other. Additionally, we are normalizing them such a way that if I take phi transpose into phi, I get I, and if these phi's this model matrix phi is of this nature, then you will get this as phi transpose k into phi as omega 1 square, omega 2 square, omega 3 square. So what it means is, somehow if we using some transformation, let's say we are able to diagonalize mass and the stiffness matrix, and then the eigenvalues can be calculated in a straightforward manner. So if we have not enforced this condition, then phi transpose m into phi again would be some diagonal matrix with non-unity values of diagonal elements, and those values you can divide through this, and then you get the omega square values. So based on this, you have a set of methods known as for eigenvalue extractions known as transformation based methods. So now when you talk of eigenvalue algorithms, so there are three ways. One is that determinant, which is you study in your even basics when you are introduced to matrices. That time you learn the eigenvalues of a matrix can be found out by taking the determinant of the coefficient matrix equal to 0 of the eigenvalue problem. So when you look at the algorithms for finding out the eigenvalues, one is, and you can actually read more and more about this. What I am discussing very briefly is from P. Sesu. If you read Bathe, you can actually learn more about it. So one is that, of course, determinant based methods. For finding out the eigenvalues. Second is whatever I just talked about here, so they are known as transformation based methods. That means we want to finally diagonalize the mass and stiffness matrix. And the third are known as vector iteration based methods. So that means we assume initially modal vector and then try to improve on it. So we are iterating on that. So they are known as vector iteration based methods. So everywhere there are so many methods. So if you look at the first one, the determinant based methods, what your general eigenvalue problem, what you are saying is that I have some omega n square, and let me talk only about some particular eigenvalues. So omega n square m into dn minus, I can write k into dn is equal to a null vector on the right hand side. Now this can also be actually transformed as a standard eigenvalue problem, either by multiplying by m inverse both sides or k inverse. So you can transform it as a standard eigenvalue problem, like essentially a into d equal to lambda times d, that kind of. So that can also be done. So what we are doing in the determinant based method, we are trying to find out the determinant of the coefficient matrix. So if you look at the coefficient matrix here, that is omega n square into m minus k. This is the coefficient matrix, and then into here you have dn. this is equal to 0. Then what we say for non-trivial solution, the determinant of this coefficient matrix must be equal to 0. So for non-trivial solution, omega n square into m minus k, this determinant of this whole matrix must actually be equal to 0. So now if you, how can you do that? So for a maybe if it is finally your assembled mass and stiffness matrices are of size 2 by 2, 3 by 3, 4 by 4. So maybe you can open up the determinant, then set up the equation in omega n square parts, and then you can solve that. Usually exact solution of that would be difficult, but then you can solve it iteratively. So what you can do is essentially start with some value. Let us say if I take the omega n value on the x axis, and here the determinant, that is omega n square m minus k. On the y axis, if I keep this determinant, so then you choose different values, you will find that when the omega n is one of the natural frequency of the system, there this determinant would be 0. So maybe initially 0 is not an eigenvalue for a, let's say some problem, then we will get the determinant could be of course positive or negative. So you would have some variations, maybe might go something like this. These can go up and down, it's not necessary like this. So see, these are the omega n values where you have the determinant equal to 0. These are the points where omega 1 value, the determinant is actually 0. So that means you can say this is your first natural frequency, omega 1, this is corresponding to omega 2, this is corresponding to omega 3, omega 4 and so on. So what you can do, but again to exactly find this out, you might know when you are choosing different values of omega 1, you might use some step size. So when you are using a step size, what you might actually find is that you have one point here where the determinant is negative, and for the next step you have determinant positive. So then you iterate between these two and exactly find out the value of omega n at which the determinant is becoming 0. So that finally will give you omega 1. And then same way you might find somewhere there is again sign change, that previous value of omega n you are getting positive determinant, and the next step you are getting negative. So again that means there is a natural frequency between these two, again iterate and exactly get omega 2. So this is these kind of methods are known as determinant based methods, and obviously they are computationally very involved, because you have to open up the whole determinant. So that itself is not actually the number of floating point operations are of the order n cube. So that itself is computationally very involved. So you hardly use this for large size system. Of course the the smaller problems of say 2 by 2, 3 by 3 matrices, you can of course do that manually, and you can actually exactly solve even rather than doing the iterations like this. So this kind of approach is known as determinant based method, which is actually not used. Then the second is, as I was talking about, is the transformation based methods. And then there are again one of the most popular one is known as Jacobi iteration method. So I am going to actually discuss that, and the idea here is if you want to read more, as I already said, you need to read because these can be courses themselves on the basically matrix algebra. So Jacobi iteration method, that is what I am going to discuss. So as I said, this transformation properties that if I have a modal vector which is actually the modal vector of the given problem, then phi transpose m into phi would be diagonal matrix. Similarly, phi transpose k into phi would also be diagonal matrix. So basic idea here is that omega n square into m into dn is equal to, you have k into dn. Now we want to diagonalize both m and k. So how can we diagonalize? Maybe we can multiply both m and k with some matrix which we call, let's say, a transformation matrix. So that transpose of the transformation matrix into m into that matrix. Similarly for k, and then through that, but then we have to appropriately choose that transformation matrix. So what typically we do in this case. So suppose we have this, let me just explain you about first K. So let us say we have K11, K12, K13 and so on. Similarly you have symmetric matrix, so K22, K23 and similarly K13 symmetric, so K23 and K33, like that. So you have this. So now what we can do is, because we do not know model vector, so we see obviously we will have to find that out, and what we know is the property that if we find out the model vector, then when we multiply that model matrix transpose into model matrix, we finally get a diagonal matrix. So since we do not know that, so we want to construct that. Now the construction how we can do is, first we can take some matrix in terms of say unknown parameters, and first make, let us say, this K12 0, that is K12 and this K21, which is same as K12. So first we will construct a transformation matrix which makes this K12 equal to 0, and similarly in M it makes M12 equal to 0. And then we move, once we have multiplied this by a certain matrix, we get a new transformed stiffness and mass matrices. Then we go and try to make K13 and M13 equal to 0. In that process, then you might of course find that when you are trying to make K13 0, maybe K12 might become non-zero, but then you repeat this whole process and again come back. So like K12, K13 up to K1n you will make 0, then K23, K24 you will try to make them 0, and so on, all the diagonal elements, and you will get certain transformation matrix. So the starting point here is a transformation matrix. Let me take T1. This is a transformation matrix T1, and T1 is chosen such a way that first we want to make K12 as 0. So that is essentially this first row and second column. So the transformation matrix K is chosen, this T1 is chosen such a way that, let us say, I have unity here, and corresponding to this, let us say, some alpha, and then I have because this is K12, so it is involving first row second column or second row first column. So I will have some beta here, rest of them unity, and all other terms are like 0 here. So you will have 0 0 here, then this is 0, diagonal elements are unity, and like that. So let me write one more here, 0 1 0 0. So you construct a transformation matrix like this. This is the size of this is going to be of n by n. Okay, so I think I'm just going to finish here because I wanted to give you an idea about this. So basic idea is that we take the transformation matrix say T1 and find out this alpha and beta such a way that when I do T1 transpose K into T1, similarly T1 transpose M into T1, the first row second column of the stiffness and also the mass matrices, they are 0. Based on that you choose your actually alpha one. So then you will get a, let me say, a transformed stiffness matrix say K1, and that would be T1 transpose into K into T1. Similarly I will get transformed mass matrix say M1, which would be T1 transpose into K into again M, not T. So this will be M into T1. So you have constructed this transformation matrix T1, that's the first starting point. In terms of two unknowns alpha and beta, then you are getting the transformed stiffness matrix, transformed mass matrix, and in this if you look at, when you do this multiplication, you will find for the transformed stiffness matrix, in this case the K12, let me say that as K12 bar, is not same as K12. This will turn out to be, so when you do this multiplication, T1 transpose K into T1, you will find the first row second column of this transformed stiffness matrix K1. This will turn out to be, so this comes as so this is going to be basically K12 bar, the first row second column or second row first column. This would be then K12 plus alpha times K11 plus beta times K22, and plus alpha beta times K12. So this would be expression for K12 bar after the transformation, that is after this multiplication. Similarly here, because we want to make this 0, so that is what I am writing. Once you get alpha beta from by making K12 bar equal to 0, you finally get actually this new matrix. Similarly, you will find M12 bar, that is that first row second column of this M1 matrix, that is transformed mass matrix, would be M12 plus alpha times M11 plus beta times M22 plus alpha beta times M12. And now you want to find alpha and beta such a way that this is actually equal to 0 and this is equal to 0. So from this you find alpha and beta. Once you find alpha and beta, then what you have is finally your T1 matrix is known, and then after you do this multiplication, you have your K1 and M1. Now again you construct another matrix T2, where you will try to make now K13, now subsequently whatever matrix, new matrices we have got, the 1 3 say K bar 1 3 and M bar 1 3, we will try to make it 0. And so here next level is you will construct say T2, and that is new transformation matrix. Since here you are trying to make 1 and 3 equal to 0, so the transformation matrix would be like 1 0, and now that would be a new value of alpha, so I am putting that in the third column, and then of course everything 0 here, and so on it will continue, and then here you will have 0 1 0 0, the things will continue. Here you will have, because it is involving 1 and 3, so the first row second column or third row first column, so I will put now that new value. Beta has to be determined again, so this is not these are not the same alpha and beta here, and then this is 0, this is 1 0 0 and so on, and then of course here then you will have subsequently 0 0 1 0 0 0 0 0 0 1 and so on. So this will be your transformation matrix. So now based on this, what you will do, you will calculate the, let us say, K2, and which would be T2 transpose into K1 into T2. Then you will get from here say K13 bar, and one equation you are going to make it 0. Similarly you construct M2. M2 is taken as again T2 transpose into M1, not M2. So this is into M1 into T2, and from this you will get an expression for M13 bar. And then now you will find new values of alpha and beta by setting this equal to 0, by setting this equal to 0. Once you get alpha beta, you get T2, you get this new set of matrices K2 and M2, and you continue this. So now you will have to do this for all the off diagonal elements once. So in this process you will find, maybe when you are completing this step, so in the previous step now we have found out alpha and beta such a way that K12 bar and M12 bar, they are 0. That is, these two we are now the first row second column and second column first row, that those terms are 0. But when you now complete this step at the end of this, when you are trying to make K13 and M13 equal to 0, so you will find new alpha beta, then construct this matrix and finally multiply, you get the K2 and M2. In that you will find now 1 2 and 1 2 element of the mass and stiffness matrices, they would become non-zero. But you don't bother about that, you continue. So no 1 2, then 1 3 2 1 4 1 5, and one round you make all the off diagonal elements 0, and then again start back from again K12. So you will if you repeat this process a certain number of times, finally you will find that the off diagonal elements would become close to 0. And once they are close to 0, then both mass and you have transformed mass and stiffness matrices, wherein only diagonal elements are non-zero, and then you find out the natural frequencies. So repeating this n number of times, finally you will get Kn, which would be equal to essentially a diagonal matrix. So it will be of the form K11 0 0. Say I'll still put some bar here, 0 K22 bar 0 0 0 K33 bar, and so that would be form of transformed stiffness matrix after n number of iterations. And similarly you will get Mn, which will also be diagonal form M11 bar 0 0 and 0 M22 bar 0 and so on 0 0 M33 bar. So once you get this, then no, like you can simply say no that your omega 1, the first natural frequency, is simply K11 bar by M11 bar, or you can say ith natural frequency square is Kii bar divided by Mii bar. So you get from this, you can calculate the your essentially eigenvalues, and then the eigenvector finally is going to be multiplication of all these transformation matrix whatever we have constructed. So finally the phi would actually be, say finally we will be having some nth transformation matrix. So this would be Tn minus 1 and so on, here T2 T1. So this would be actually your modal vector. So this of course requires a certain number of iterations. So for my PhD students, the eigen and d-eigen, that is what I use in the other set of programs, that is actually based on this. And of course we use the another algorithm which is Lang-Sauce. So that one of these we are actually using that, some of our codes we actually use this. So this is how you use the Jacobi matrix. So what I have told is a brief introduction that you start with this eigenvalue and you want to diagonalize the mass and stiffness matrix. So you construct this kind of a transformation matrix, and then at a time making one off diagonal element equal to 0, you find alpha beta and continue this iteration. When you do that sufficient number of times, you finally get this and diagonal mass, diagonal stiffness matrix, and therefore easily can calculate the natural frequencies, and then the modal vectors are just the multiplication of all the transformation matrices you would have used to transform the stiffness and mass to diagonal matrices. So this is one. Then one more maybe an example of vector iteration method I will discuss in the next class, and then I will start basically the error analysis and convergence. Anyway, this eigenvalues are